Hello and welcome to part 3 of Dev Maths and Stats Refresher Course, Lecture 5. Now we're going to look at differentials. This is quite a useful topic in its own right because you'll meet it in lectures and articles and books, but also it's an important building block for all the rest of this optimization material. So what we've seen so far is that if you differentiate a function of one variable, that tells you the gradients of the tangents to that function's graph. So you've got the gradient of the tangent from differentiation. When you have two variables, then the partial derivatives, be partial dx, partial dy, gives you the slope of the tangent plane to that function's graph. Now that's really useful if you want to know what happens when one variable changes, how that's going to impact another variable. And the idea of this using differentials is that we're interested in when the variables change, the value of the function is going to be close to the tangent, at least for a short distance. So what we're interested in here is when that's going to be a good enough approximation to tell us something interesting. So in some situations it will be, in some situations it won't be, as we'll see. So let's look at some particular examples. So we define a function, quadratic function, and we have to pick a starting point, so let's say x is 3. And you want to know what's the impact of increasing x. And what we'll do is we'll consider two possible changes in x, a small one, 0.2, a larger one of a whole unit, and see what the impact is on x, on f of x in each case. So we need to know what we're starting with. So we're starting with a function at value of 3. So substitute 3 and get 30. And we need the gradient of the tangent. So we differentiate f, so we're going to get derivative of this, and then put in x is equal to 3, and you find 4. So the slope is 4. That means that at the point x is 3, if we increase x by a unit, the tangent goes up by 4. Okay, so we're going to use that to predict what's going to happen to f as we increase x. So if we have a small increase of 0.2, so from 3 to 3.2, we expect a rise in f of 0.2 times 4, because 4 is the gradient at that point. So we expect it's going to rise by 0.2. So the function at the point 3.2 should be approximately 30, which is where you start, plus 0.8 gives you 30.8. Now let's look at the larger rise when we're going to increase by a whole unit. So that takes us from 3 to 4. The rise in f is estimated as 1 times 4 units, because the gradient is 4, which gives us 4. So the function x equals 4 should be 30 plus another 4, it should be 34. So what we've done is we've started at the point of 30, we've used the gradient of 4 to predict the value of x ahead without calculating. And I predict it's going to be 30.8 at the point 3.2, and I predict it's going to be 34 at the point 4. But now, because we know the actual function, we can compare the values. Okay, so we can see that they are both overestimates, but the first one is closer because the first one I predicted 30.8 and it's really close, 30.72. Second one I predicted 34 and it's really 32. So it's not so good, the second one. So of course we can just draw a picture here to see what's going on. Okay, so we started at 3 and essentially by using the gradient, we're following this red line instead of the black line. So we can see that at the point 3.2, the red line and the black line on this scale, I can't tell the difference, they're so close. But when you come to 4, then you can see there's a bit of a gap. So that was 34, the 32 that I should have got, and this is the 34 that I predicted over here. That's why I missed out. So at least we can say that though the approximation is not so good here after a whole step to 4, at least the direction of change is okay. I correctly predicted it would increase. So can you just pause and think, would that be true for any size of increase, that I'm going to get the correct direction? So hopefully you pause there, and the answer is no, it wouldn't be, because if I start from 3 and I had an increase of 2, I would have predicted the red line, a huge increase here, but in fact the reality would be I'd be here, so I'll hardly increase at all. And if I took an even larger rise, I would be predicting something of, if I took a larger rise in x, I would predict a very high value for f, where in fact it would be decreasing. So after a certain period of time, the predictions become completely nonsense, totally useless. So we want to stay quite small. Right, let's just repeat the same thing with a function of 2 variables, and then hopefully imagine how it generalizes to the situation that you guys have to deal with about 15 variables in the real world. So here is a function of 2 variables, again a quadratic. Again, choose a starting point, so just randomly choose 15 and 33 for x and y. And the value of the function here is 111. So put x, 15 and 33 into here and we find 111. So that's where we start from. Next we need the partial derivatives, and now we have two partial derivatives because we have x and y. So differentiate those as you've done now many times before to find the partial derivative functions and substitute in the particular point we're at, and we find that at that point the gradients are -12 and 14 in x and y directions. Now we're going to have to pick 2 changes to look at, so I want a small change to start with. And here we have 2 things that can change, x and y, so I have to decide how much they're going to change by. So I'll have 0.2 in x and 0.4 in y, so that's quite small. And then a bigger increase will have increase of 1 in x and increase of 2 in y. So start with a small increase. If you go in the x direction 0.2 from the initial point, which was 15, then this is telling us that the rise in the function should be 0.2 multiplied by -12 is -2.4, because in that x direction the function is actually sloping down. Right? So I expect to, because I'm going in the x direction, I'm going to have a fall of -2.4. On the other hand, when I move 0.4 in the y direction, I get a rise of 0.4 times 14. So that takes me up 5.6 units. So the total value of the function at this point here, I've added on the 0.2 and the 0.4, it's going to be 111 starting point. Take away the 2.4 because I'm going down in the x direction, add the 5.6 because the y direction is going upwards, I get to 114.2. Okay, here, I won't talk through the same calculations here, but the same calculations for the larger rise give you a fall of 12 and a rise of 28, should take you to 127. So again, you're predicting a rise. So my 2 predictions are 114.2 and 127. As before, we know the actual function, so we can substitute in. Okay, and we find, okay, again, the first one is 140.2, 114, yeah, it's really close. And the second one, 127, 134, is quite some way out. So again, the first one is better, but this time, both of them are underestimates. Unlike here, when both were overestimates. In this case, it's because they are underestimates. You might like to guess why that is before we draw this graph. See if you can predict why I've got underestimates. And then we'll have a look at the graph to see. Okay, so here's the graph. Oops. So sorry, that might have skipped because the tangent plane did not appear. But here we've got the function is the curved surface, that's the function g, and the tangent plane here is the flat surface. And the tangent plane is drawn to touch the curve at exactly the point x is 15 and y is 33, so that's the point here. That's where it's touching. And then both the increase that we did, we're moving away from that point, but to get the estimate using the derivatives, we're moving on this black tangent plane instead of moving on the surface. So you can see that's why in both cases, this time it's below. That's because the graph is convex instead of concave. It's bending upwards away from the tangent, whereas the previous one was bending downwards like that. So that's why they're underestimates. But as before, you can see that as you move further away, then the plane is getting further from the surface, so the approximations are less good. Now, these kind of approximations, we can express those using what's called the differentials. Now, an actual change in any variable, a quantifiable change, can be written as delta A, this Greek symbol delta, and you'll see that all throughout the year. Economics, impact evaluation, you'll see that everywhere. Because this is essentially what you're trying to find out. How do things change when you change something else? Now, a differential change in variable A is written as dA. And this can be thought of as meaning an approximation using the tangential method that we've discussed so far. And when delta is small enough, then dA is a good enough approximation for our purposes to tell us something interesting. So let's get some general rules, which is, in the single variable case I just gave you, I was saying that this linear approximation of a change in df, is 4 times the change in dx, because the gradient was 4. If you look back, you'll see that's what we're doing. So we're just multiplying the change in dx by 4 to get the predicted change in df. That's just at the point x equals 3. For any point in that function, instead of 4, you'd have this, which is the derivative. And for any point on any function at all, you have the general sign for the derivative here. So this equation sort of looks as though it makes sense as an equation with fractions, because you can cancel out the dx's, but of course this isn't really quite a fraction, but it looks as though it makes sense like that. So df is df by dx times the change in the change in x dx, sorry. Then for two variables, a similar thing is this. So the predicted change in df at that particular point was negative 12 times the change in dx plus 14 times the change in dy, because these are the gradients in the x and y direction at that particular point. For any point on that particular curve, on G, then you can put in the two partial derivatives with x and with y there. So that works for any values of x and y. And then for any point on any function, you have this kind of situation where the change in df is equal to partial derivative with respect to x of f times the change in x plus the partial derivative of f with respect to dy times the change in dy. Now, before we finish this video, I can show you that this thing here you can write in an alternative form using linear algebra. And this is what first made the connection between the calculus and the linear algebra from the last lecture, which is that if you define some vectors like this, so you define a vector which is these two small changes, the differential changes, small changes in x and y. So that defines how much we're going to change our position by. This then is called the gradient vector, which is a vector where the two components are the partial derivatives of the function with respect to the two variables. And if there's more than two variables, then you can have more, a longer column function. But with two variables, you have this partial derivative with respect to x and y are the two components. Then the linear algebra bit is saying that this equation up here for the change in f is just equal to this dot this, the scalar product. This dot this gives you this, because it's that times that plus that times that. So you've got a neat way of writing with linear algebra the estimated change in f, which is the dx by dy dot the gradient function of f. Okay. Before ending this video, because we'll deal with this in the next video, before ending this video, I want to just go to point to a couple of the visualizations which are in the collection for today. There's this one here, which is the simplest one, which is just showing you that this is for function x cubed plus 1, starting at this point. Here's an estimate, and it's showing you that there's an increase in x. This is the delta y is the actual increase in y. From 1 to 2, the actual increase is right up to here. So if we predict this by going along the tangent, so you multiply, so it's an increase of 1 times the gradient, then you predict you get to here, dy, which is this. So it's the gradient times the increase, predicts this, but in actual fact, the increase is this, so it's completely wrong, much too small. But as you decrease the step forward down to this much, if it's really close, it's a very small increase of just 0.3 or something, then the predicted increase is this, and it's getting much closer to the actual increase in the function. It can go as close as you like. Down very, very, very close. So for very small increases, it gets very close. This here shows you that it's almost the same thing. It lets you change the starting position as well as the distance you go forward. I like this one because I can show you that. You can see that it's not very accurate here, but if we do the same step forward of 0.7, starting from a higher number, it's giving you a closer approximation. If we start from a number down here somewhere, though, the approximation is very bad. It's a bigger miss, and that's because the graph is getting more curved. If you go all the way down to there, then the prediction becomes nonsense, because the prediction is no change, and in fact it's gone up. So depending on the curvature of the graph, it's more or less accurate. This is just to remind you that in 2 dimensions it's more complicated to visualize. Here's a point A I can move to show combinations of x and y. So I suggest you have a play with this. So if you can play with this diagram and get a good idea of what the different things mean, that will really help you visualize the later stages. So here's the combinations of x and y. And at the moment it's just showing me here on this grey plane where I'm moving, and b is then the height of the actual function, which is this x squared minus y squared. So at this point b is quite high. As I move a back towards here, it goes down like that. The function decreases, then it increases, gets very large here. If I come back this way, you can see it decreases very, very rapidly and goes negative very quickly. So it's very, very steep here. It's less steep around this point here where it's equal to 0. So that's just showing the red point is the height of the function at the blue point. Now I can look at how it's changing in each direction. So if I look at the fx tangent, the red line is just all the points that have got that same x coordinate. So I could try and move along that. Oops. Sorry, all the same y coordinates. So I'm moving along the x-axis. And then this is the tangent to that in the x direction. So it shows that here, if I increase x, I'm going down the function is decreasing very steeply. Here it's quite shallow, and here it's increasing very steeply. And you can do the same in the y direction, which is this way. Oops. It's difficult to draw. You must have a go at this yourself. So here it's increasing quite little, and then there it's decreasing very rapidly. Okay, so you've got, this is the slope in the y direction, the other one's the slope in the x direction. What makes the 3 dimensions harder is that it's not that you increase from one direction to 2 directions, but really you can go in any direction, because you really have a tangent plane. You can move in the x direction or the y direction or any combination of these. So with your linear approximation, you're going along that flat surface in any direction, which is why, as we'll see, it becomes much harder to really predict what's going to happen. Yeah. So you can see sometimes you're going to get an overestimate, sometimes an underestimate, because you're using that flat surface, like Captain America's shield, I think, so not quite the same idea. You're moving along that surface instead of the curve. And here's a picture of the gradient vector visualized. So here, I hope that you're good at understanding maps. This is as though you're showing a 2-dimensional map of a 3-dimensional function. So you have to imagine that this is like a valley. So here's the bottom of the valley, because this function here is 0 at the point 0, 0. At this point here, it's best to show the value at x equals 2. Roughly there. So yes, okay. If you take x is 2 and put it into here, and y is 0, so forget the y's, your 2 to the power 4 is 16, plus 2 is 18. So here around your point 18. And this red line represents all the points that would give you 18 as the value of the function. So that's the highest point we're shown, and these points are all lower. So the function is increasing. So each green contour shows the constant value of the function. So we're looking at points on this blue one where it's fairly low, and what we do here is we calculate the 2 partial derivatives. So you get the partial derivative with respect to x and y, and substitute in this value to get the two numbers. So we can see, I think it's 0.99 and 0.82. Oh, no, here we go. Here are the two. Here are the two partial derivatives. So here, if you, the two components of the partial derivative, if you plot them, that grad derivative, the gradients function, the gradients vector is going in this direction, which means that as you go in the x direction, the function is increasing very quickly, but in the y direction, it's not really, it's quite flat in the y direction. That's why this vector is pointing this way. And it always points down the slope the steepest way it can get. So as you move around, it's pointing directly down the slope. Down here, the decrease in the x direction and the y direction are about the same, so it's pointing like this. This is where it gets so long, goes off the graph because it's so steep here. In this place here, it's changing much more in the y direction than it is in the x direction. The final thing to notice here is that because if I want to keep this, the value of the function constant, I've got to go along this blue line. So the blue line is at right angles to the direction where the function is changing the most. We'll come back to that later in the optimization part. Okay, those are just some visualizations. I hope you find those useful. Otherwise, if not, I hope that you zoom through them with fast forward. But in the next section, we'll look at the idea of total differentials and actually finding some more differentials. But for now, thanks for watching.